All right, good afternoon, ladies and gentlemen. I'm Christopher Januzzi, ECS Executive Director and CEO, and it is my great pleasure to welcome all of you, whether you are here on site with us in beautiful Vancouver or joining via video stream from somewhere else in the world, to this, the 241st ECS meeting. How exciting to be back together again. It has been a long time, a very long time, since I've seen this many people, especially this many ECS people, in one place. And looking out over the crowd right now, I can honestly say that you really do look a lot better in person than you do on Zoom. It's nice to see you in 3D, so thank you so much for being here. Yeah, this is great. For 120 years, yes, the Society is now 120 years old. ECS meetings have been the premier technical conferences in the electrochemical and solid-state fields, showcasing the visionary work of students, faculty, researchers, practitioners, current Nobel laureates, and I think it's a fair bet to say future Nobel laureates as well. In this meeting, we'll carry forward the ECS's legacy of outstanding technical content. We have 45 symposia with over 2,500 abstracts, including 1,700 oral talks, 400 posters and 400 digital presentations, and more than 1,000 student talks, all coming from 66 countries. With numbers like this, it's clear to see that if your interests are in electrochemistry or solid-state science, you will find what you are looking for here in Vancouver this week. We kicked off the meeting yesterday with a lovely reception for ECS members, and this is something new we tried because it has been a while since we've been together, as I said, and we wanted to do something special to celebrate our return to in-person meetings. And it certainly was a special event. So I think this is a feature that you will see us continue at future ECS meetings. But of course, we also like to welcome all of you who have not yet had the chance to become ECS members, and we hope to see you at our next ECS members only event, which will be at the fall meeting in Atlanta. And in the meantime, though, please let us know if there's anything that we can do to help you make the most of your experience while you're here with us at this conference. Take the time to learn more about the Society, how you can join, support, and benefit from engagement with this amazing organization. The conference exhibition opens immediately after this event, so stop by the ECS booth to meet with the staff, and while you're there, please be sure to visit with all our exhibitors who have joined us here in Vancouver this week. ECS is incredibly fortunate to have a diverse array of sponsors helping bring these events to you, and I would like to recognize them now. First, a very special thank you to our friends at Waters TA Instruments for sponsoring today's plenary with Professor Jeff Dahn, helping to make the wonderful lecture we are about to hear possible. And of course, we are so grateful to our many general meeting and symposia sponsors. It is only through their support that we can offer the robust technical program and the enriching special events that you'll find here at the meeting this week. I'd also like to give a warm welcome to our institutional members, shown here, whose support through ECS annual organization memberships is critical to our work that we do. Our institutional membership grew by 15% this year, a trend we would very much like to continue. And it's interesting to note that many institutional member representatives are here attending the 241st meeting through the complimentary registration benefit afforded to our institutional partner. So if you want to learn more about being an institutional partner, you can see us in the ECS booth right after the plenary today. It would be impossible to produce these meetings without the support of ECS's divisions and sections. Not only are the divisions ECS's technical front lines, creating the communities and the content that make ECS the organization it is today, but divisions, along with ECS sections, are a vital source of financial support for our meetings. And this year, the divisions, along with the Texas and European sections, provided nearly $50,000 in travel support to over 100 students and early career attendees. And we have additional travel grants made available this year, made possible through the generous legacy donation of the estate of past ECS President Theodore R. Beck, and administered by the IE and EE division. Dr. Beck joined the Electrochemical Society in 1954 and was active in local, section, and division and society affairs throughout his distinguished career, which included positions at Kaiser Permanente, Boeing, and ultimately his own research consultancy, Electrochemical Technology Corporation. He authored 77 technical papers and received 11 patents. We are honored and humbled to be remembered by Dr. Beck this way. His gift to ECS will enable students and early career researchers to benefit from engagement with the society, just as he did, for years to come. And I think it's a really fitting tribute to and from one of our own. And so we offer our sincerest thanks to Dr. Beck and all the Beck family for their enduring support. In closing, I would like to wish you all the best this week here in Vancouver. And I will ask you to join me in welcoming the director of the Maryland Energy Innovation Institute, the William L. Krentz Centennial Chair in Energy Research, and a distinguished university professor from the University of Maryland, and I might add, the pride of San Rafael High School, ECS President, Professor Eric Waxman. Mr. President.
Thank you, Chris, and thank you to all of our attendees for coming to this beautiful meeting in Vancouver. I cannot tell you how excited I am to officially open the conference and to be able to welcome you to the first in-person meeting of the Electrochemical Society since October 2019. That seems so long ago. I came to my first ECS meeting in 1989. That was even longer. And since then, these gatherings have been an absolutely vital part of my professional life, introducing me to the colleagues, collaborators, and friends that have helped shape my career over these past 3 decades. And I must also add, have been a major part of my family life. You might notice some of the pictures and my wife and daughter over there. As my first order of business, I would like to extend my thanks and gratitude for the leadership of my predecessors, Christina Bach and Stefan de Gent, who, along with ECS volunteers and staff, produced the 3 outstanding digital meetings we hosted to keep us connected and to keep science moving forward during the COVID-19 shutdown. But I have longed for the direct personal face-to-face connections ECS meetings like this provide, and so I'll return to in-person meetings as cause for celebration, and celebrate we will. However, we do so with heavy hearts for our friends and colleagues in Ukraine, who at this very moment are valiantly fighting for their country, their homes, and their lives. We all watched with horror back in late February when the invasion of sovereign Ukraine started. Since then, the resiliency, courage, and determination of the Ukrainian people has been a source of hope and inspiration to all of the freedom-loving people of the world. Shortly following the invasion, I, on behalf of the ECS Board of Directors, issued a statement expressing our collective shock and dismay at the appalling actions that occurred. And although this society's mission is not political, we were compelled to share this statement because what is taking place is a humanitarian tragedy launched without provocation or regard to the needless suffering the invasion has caused. In addition to issuing this statement, I have personally written to all of our constituents in Ukraine to offer them complimentary ECS membership and registration to our meetings taking place in 2022. We realize those in Ukraine are dealing with dire, life-threatening circumstances right now. We made this offer in hopes that ECS membership and access to our meetings will provide some sense of solace and connectedness in these most trying of times. The response from our friends in Ukraine has been overwhelming. I can't tell you how many emails I've received thanking us for that. And also, we want to thank them and welcome them who are live streaming as we are today. And to our colleagues in the Russian Federation, ECS acknowledges that the actions taken by your government do not reflect the will of individual ECS members living and working there. We hope that you stand with us in our complete denunciation of this horrific action. My friends, we find ourselves living in a very different world than when we last met. Over 6 million lives have been lost to COVID-19. There's political and economic upheaval on a global scale, and climate change continues to wreak havoc on an already overstressed world. Each of us, no matter where we live, is being directly and severely impacted by these events, making absolutely clear that when it comes to addressing the grand challenges facing the world today, we are all in this together. And that fact gives me great hope, because not only is the work of the ECS community central to addressing these global grand challenges, but with representatives from 66 countries, the world is here at this meeting, united in our commitment to finding solutions. Through science, we will overcome these challenges. Together, we will continue to do what ECS has done for 120 years and counting, convene the leading technical minds to advance our science for the benefit of all humanity. Tonight is our pleasure to honor members of ECS for their contributions and to celebrate. I told you it was coming. And because this is our first in-person ECS Awards and recognition ceremony in several years, we have a bit of catching up to do. And so, in addition to this year's awardees, we will also be joined by those who've received awards since we last came together. First, I would like to congratulate our divisions and section award winners, whom you will find listed both online and in the meeting program. Please make a point to attend their sessions where you can experience firsthand why they are being recognized by their peers for their technical contributions. Our first award is the Leadership Circle Award, which recognizes and thanks our institutional partners in electrochemistry and solid-state science. The award is granted in the year a member institution reaches a significant anniversary milestone. Today, we recognize the following institutional members for their 25 years of dedication to ECS. Scribner Associates, represented by Kevin Cooper, and Electrosynthesis Company, represented by David Genders. Thanks very much to Kevin, David, and their firms for their continued support and engagement. And now I would like to ask the ECS Second Vice President and Publication Subcommittee Chair, Jerry Bott, to present our next award.
Thank you, Eric. And today I will be presenting the Norman Hackerman Young Author Award, which is given annually for the best paper published on the Journal of the Electrochemical Society by young co-authors in the preceding volume year. With us today is the 2020 winner of the Norman Hackerman Young Author Award, Stefan Oswald, from the Technical University of Munich, for the paper, Novel Method for Monitoring the Electrochemical Capacitance by In Situ Impedance Spectroscopy as Indicator for Particle Cracking of Nickel-Rich NCMS, Part 1, Theory and Validation. Congratulations, Stefan. And now I would like to ask ECS President-elect Turgut Gur to come to the next stage to recognize our next recipients.
Thank you, Jerry. Thank you, Jerry. Good afternoon. The 13 divisions of the ECS ensure in-depth coverage of the Society's broad technical domain. Over the course of their 2-year terms, division chairs not only oversee all affairs of their respective divisions, they also provide stewardship at the Society level by serving on their board of directors. As part of the board, these chairs helped shape the future of our organization, and so we are truly indebted to them for their service. Please join me in recognizing the following past division chairs. Greg Jackson, High Temperature Energy Materials and Processes Division Chair from 2017 to 2019. John Stacer. Hold your applauses until we're all finished. Thank you. John Stacer, Industrial Electrochemistry and Electrochemical Engineering Division Chair, 2018 to 2020. Slava Rotkin, Nanocarbons Division Chair from 2016 to 2020. And Marko Duf, Battery Division Chair from 2018 to 2020. Please join me in a round of applause to thank the division chairs for their service of ECS. And now we will recognize 2 members who have served in the executive leadership of ECS through their work as society officers. First, Jim Fenton, ECS Secretary from 2016 to 2020. And we would like to recognize the 2020-2021 ECS President, Stefan de Gent. Jim and Stefan, the Society offers our sincerest thanks for your leadership, insight, and inspiration. Thank you. The distinction of Fellow of the Electrochemical Society was established to recognize advanced individual technological contributions in the field of electrochemical and solid-state science and technology, as well as active membership or citizenship involvement in the affairs of the Electrochemical Society. While we normally announce the class of fellows at the fall meeting, as Eric has mentioned, we are behind in acknowledging our newest fellows. So to catch up today, we are pleased to be joined by two members of the 2020 class of ECS fellows, Catherine Ayers for her leadership and technological advances in electrochemical energy systems, and Kang Xu for his electrolyte materials development and fundamental understanding of interfacial electrochemical mechanisms. Catherine and Kang, this is our society's honor to welcome you both as fellows of the Electrochemical Society. Now I leave it to you. Thank you.
The Henry B. Linford Award for Distinguished Teaching was established in 1981 for excellence in teaching in the subject areas of interest to the Society. Henry Linford was a distinguished professor of chemical engineering at Columbia University and known for his work and research in electroplating and corrosion of metals. We have two winners we are recognizing today. The first is the 2020 Linford Award winner, Ram Mantharam. Ram is receiving this award for teaching, mentoring, and nurturing numerous students through lectures, laboratory experiments, and scholarly writing on new materials design. Professor Mantharam gave his award talk, Intricacies of High-Energy Cathodes for Lithium-Ion Batteries, via webinar in June of 2020. The talk is available to view on the ECS website. Congratulations, Ram. The 2022 recipient of the Henry B. Linford Award for Distinguished Teaching is Martin Winter. Professor Winter is receiving this award for outstanding accomplishments and excellence in teaching electrical energy storage science and technology, and exemplary support of the mission of the Electrochemical Society to disseminate knowledge and promote electrochemical science and technology in the public interest. Professor Winter delivered his award talk, The Role of Electrochemistry in Battery R&D, earlier today. Congratulations. The next Society Award, the Vittorio De Noro Award, was established in 1971 to recognize distinguished contributions to the field of electrochemical engineering and technology. Dr. De Noro is known internationally for his many contributions to industry, particularly in the manufacturing of chlorine and in the development of dimensionally stable electrodes. The winner of the 2020 Vittorio De Noro Award is Hubar Gastert for distinguished research and education contributions to electrochemical engineering and its applications to advanced fuel cell and battery technologies. Professor Gastiger presented his talk, Analysis of the Catalysis Requirements with regards to catalyst structures and catalyst durability studies for PEM water electrolysis at Prime 2020. And the 2022 Vittorio De Noro Award recipient is Robert Savinel for a long and distinguished career of fundamental and applied electrochemical engineering, research leading to new electrochemical materials and devices, training new electrochemical engineering researchers, and inspiring the start of national and international research programs in new electrochemical technologies. Professor Savinelli's award talk, Electrolytes, Discovery to Fundamentals and Fundamentals to Discovery, takes place on Wednesday at 11:40 a.m. in room 213. Congratulations again to all of today's award recipients and service recognition honorees, and thank you for your contributions to the science and the society. Now it's my pleasure to introduce today's plenary speaker, Professor Jeff Dahn. Dr. Dahn is Professor, Canada Research Chair, and NSERC Tesla Canada Industrial Research Chair at Dalhousie University, with dual appointments in the Department of Physics and Atmospheric Science and Department of Chemistry. He's recognized as a pioneering developer of the lithium-ion battery using worldwide in laptop computers and cell phones and Tesla automobiles. His recent work focuses on increasing the energy density, improving the lifetime, and lowering the cost of lithium-ion batteries. A member of ECS since 1991, the Society has recognized his research by presenting Professor Dahn with the 2006 ECS Canada Section Electrochemical Award, 2001 ECS Battery Division Technological Award, and Fellow of Electrochemical Society in 2012. Other national and international awards bestowed upon Professor Dahn include the Fellow of the Royal Society of Canada in 2001, the 2017 Gerhard Herzberg Gold Medal in Science and Engineering, Canada's top science award, and Officer of the Order of Canada in 2020. In the last 5 years, Dr. Dahn has co-authored well over 100 articles published in the Journal of Electrochemistry including his most cited work to date, a wide range of testing results on an excellent lithium-ion cell chemistry to be used as benchmarks for new battery technologies. Together, these works have had enormous impact on our science, garnering nearly 5,000 citations. Please join me in welcoming Professor Jeff Dahn for the ECS Plenary Lecture on Modern Lithium-Ion Batteries, More Than 1 Million Miles and Possibly a Century of Life, sponsored by Waters TA Instruments.
Thank you. Well, I'm honored to be here to give the ECS lecture, and I thank the Electrochemical Society for the opportunity. I really want to focus today on how to make a very long lifetime battery. And I want to really try to show you why it's important to do that. So I want to start by talking about the ways we can produce, measure, and store energy. Oh, forgot this. So I want to just give some shout out to the people who contributed to this work. At Dalhousie, the people listed here, and really Connor Aiken and Tina Taskovic did the heavy lifting, and contributions from Tesla and Novonix. So I want to start by talking about what is a kilowatt hour, a unit that we can use to measure energy. If you use a toaster for an hour, it draws about a kilowatt hour of electricity, and if you run it for an hour, that would represent a kilowatt hour. You can store a kilowatt hour of energy by raising a metric ton of water or rock 360 meters, and you can recover that energy when you let it down if you turn a cable by the descending rock running a generator. If you freeze 10 kilograms of water, you'll store a kilowatt hour of energy in that frozen water that can be used to cool things later on. You can heat 10 kilograms of bricks to 425 degrees C, and that will store a kilowatt hour of energy as heat that you can recover later by blowing air through that heated brick stack. 7 meter-seconds of wind passing through 2 meters squared for an hour generates a kilowatt hour. Sunlight striking 4 meters squared at the Earth's surface for 1 hour, assuming 25% efficient solar cells, generates a kilowatt hour. If you drive a typical 5 kilometers in a typical car, you'll expend a kilowatt hour. Gasoline is very energy dense. 100 milliliters of gasoline will provide a kilowatt hour of energy. And finally, the energy stored in 2 liters or 4 kilograms of charged lithium-ion batteries approximately can store a kilowatt hour. And in my province, electrical energy is about 18 cents a kilowatt hour. It's pretty darn cheap when you think about it, actually. So I want you to remember these numbers as we go through the talk. The world energy use in 2020 from all sources, about 160,000 terawatt hours. This represents energy used for transportation, for heating, for industrial uses, everything. And if you divide this by 365, and then also by the number of hours in a day, you learn that the world is using about 20 terawatts of power at all times throughout the year. And if you want to know if these numbers make sense, you take 20 terawatts times 24 hours in a day times 365 days in a year, and you get a number, excuse me, very close to 160,000. Now this chart shows the way that the energy used in the world, where it comes from. And when you look at it, you'll see there's coal, oil, and gas. There's about 130,000 terawatt hours of that 160,000 that comes from fossil fuels. And in 2050, to reach net zero, we have to replace all of this by renewables or some other source of energy. So this is really a pretty depressing graph. It shows the magnitude of what we're facing. We need to eliminate this 130,000 terawatt hours of fossil fuels. And of course, as the world's population grows and the standard of living increases, it might get much more, but thankfully coal and oil seem to be flattening out, but natural gas is still going up. So renewables like solar and wind are cheap and abundant. They're being installed rapidly worldwide. The obvious problem is that the sun doesn't always shine and the wind doesn't always blow. So we need energy storage, and we need it big time. The numbers I'm talking about are massive, huge. So what are some of the sensible options that we have? Well, one very good way is pumped hydroelectric storage. You pump water up a hill when renewables are abundant. You go back down and run a generator when renewables are not abundant. This is a picture of a facility in Pennsylvania, and these things are large. The largest one in the world is in Bath County in Virginia. It can store 30 gigawatt hours of energy, and can discharge in 24 hours. It's actually perfect for my province if it were sited there, because we use 20 gigawatt hours per day. So we could store all the electricity we need for a whole day in this particular system. The efficiency is about 70 to 80%. It's very, very decent. And the cost is the lowest of all energy storage systems. The problem is that the energy density based on gravitational storage is very, very low. So the upper reservoir in Bath County is 265 acres. The water level changes by 110 feet between charge and discharge. And the head height between the lower and upper reservoir is 380 meters. So you don't have to think very long to think that there's limited sites like this in the world. But every single one that we can access should be deployed. And like I said, pumped hydro stations are so huge because you have to elevate a ton of water, a height of 360 meters, to store only a single kilowatt hour. You don't always have to store you don't have to store energy as stored electricity. If you're using it for heating, you can store it as heat. So there's something called electric thermal storage, and in our province, 20,000 Nova Scotians have it. It's a system where you have heating elements like you would find in the bottom of your oven that are interleaved between a brick stack. And when the price of electricity is low, or when renewables are abundant and you need to have heat, you heat the bricks. And then when the price of electricity is high, or when renewables are unavailable, you run forced air through the brick stack to heat your home or your industrial setting. In many parts of the world, air conditioning represents a huge energy load. In Florida, 27%, Qatar, 60 to 70%, Israel as much as 42% used for air conditioning. So we need the equivalent of heat storage, but we need cold storage. So solar and wind can freeze a phase change material to deliver cooling when the sun is not shining or the wind is not blowing. Storing cold as cold would limit the need for electrical energy storage. So there's this really cool company called Nostromo Ice Brick. They're listed on the Tel Aviv stock market, and if you go look at their website, it's pretty cool. So they have this system where they have these chambers that are filled with plastic discs that are hollow, and inside the plastic discs, they've encapsulated water. So when it's time to store cold energy, you run a refrigeration system and pump cooled fluid, through this stack of discs and freeze the water in the discs. And then when you want to cool your building, you run water or fluid, through this stack and cool the fluid as it goes through, as the ice in the discs melt, and you cool the building. So this is a good way to store cold as cold, if you like. So these are sensible ways to store energy for the uses that it could be intended. But lithium-ion battery storage is probably the most popular way of storing energy today. This is one example of hundreds of lithium-ion battery storage systems that you'll find. It's in Ontario. The Oneida First Nation has set up this large 1 gigawatt-hour storage system there. And lithium-ion batteries are by far the most implemented electrical energy storage system today. And this is for a variety of reasons, including simplicity, smallest footprint, and cost. And I'm going to talk about lithium-ion batteries, obviously. You know, that's what I do. So for this audience, I'm not going to spend time talking about the details of a lithium-ion battery. I'm going today to speak about lithium-ion batteries that are based on 3 different positive electrode material types. They're all, 2 of them are layered lithium transition metal oxides, so lithium, nickel, manganese, cobalt oxide, where in one, nickel is 50%, manganese 30, and cobalt 20. That's called NMC 532. The other one, NMC 811. And then I'll also talk about lithium iron phosphate. And lithium-ion batteries, as we know, they have the highest energy density of any ambient temperature rechargeable battery system. They have a long lifetime. They have almost no self-discharge. They come in convenient sizes and shapes. They're affordable, and a short recharge time is possible. So in September of 2019, we published this paper in JES, and Eric mentioned it in the introduction. I didn't know he was going to do that. But it has a title that's not very catchy. You probably would not even want to read this thing when you look at it. You'd say, okay, fine. The reason we published this paper and the title that it has is because we got annoyed by researchers and startup companies publishing results on their particular battery chemistry and comparing it to crappy lithium-ion data. And then stating, oh, our stuff's better than lithium-ion. So we published this paper to try to show what a good lithium-ion battery could do. Now, because my research group is funded by Tesla, the media follows what we do very carefully. Oh, but in the abstract of this paper, I wrote, we conclude that cells of this type should be able to power an electric vehicle for over 1.6 million kilometers, 1 million miles, and at least 2 decades in grid energy storage. And the media picked up on this. And the very next day, this appeared, September 7, in Electrek. Tesla battery researchers unveils new cell that could last 1 million miles in robot taxis. So the so-called million-mile battery was born. So in this paper, we showed testing results for, several years of testing where cells accumulated 3,000 or 4,000 cycles. And many of the cells in that paper, we left them on testing from 2019 till the present. And they've racked up a lot more charge-discharge cycles in the meantime. So here are 3 years of testing results on these batteries. They use a so-called single crystal NMC 532 positive electrode material with graphite negative. They're operating here at room temperature. They're doing a 1-hour discharge and a 1-hour charge. And they have what we call a rate map every 100 cycles. We'll start with this panel over here on the left side. So these are small lithium-ion pouch cells, and they have about 160 milliamp hours capacity at 1C when you're running them to a charge of 80% state of charge, or 4.1 volts. And you can see over these 10,000 cycles, with 3 years, there's virtually no degradation at all. If you charge to 4.2 volts, which represents 90% state of charge, again, there's very little degradation, but slightly more. And if you charge to 100% state of charge, or 4.3 volts, you can see things are still very, very good. And if these were used in an electric vehicle and it was a moderate range vehicle, if every cycle were 350 kilometers, this would be 3.5 million kilometers. It's incredibly long, right? So I'm not going to go into the details of what you need to do to make a battery like this. You can look in the Harlow paper for all the details if you're interested. I decided in the last conference I attended to update this data for the cell on the left. So in March of 2022, that cell had reached 14,000 plus cycles with 5% degradation at 1C, 1C. So incredible, and it's going to stay on until the charger breaks or the cell fails. So in that Harlow paper, we made projections for the lifetime of these cells at both 20 degrees C and 40 degrees C, and we did this by combining the results of charge-discharge cycling experiments with storage experiments. And at 20 degrees C, if you follow the black line, we're plotting the fractional capacity that the cell would have if it were undergoing just one charge-discharge cycle a day with a 3-hour discharge and a 3-hour charge. And after 25 years of testing, it would have about 90% of its capacity remaining. If it were used in a vehicle and there were 350 kilometers for every charge cycle every day, it would drive about 3 million kilometers in that 20-plus year period. And lithium-ion batteries degrade more rapidly at higher temperature. This is because there's unwanted parasitic reactions that occur between the charged electrode materials and the electrolyte. Very small, but they accelerate with temperature. So at 40 degrees C, you're basically looking at 10 years of life till 70%. So these lifetimes are pretty decent, but how do we make them even better? And that's what I want to talk about today. So what's important for developing long lifetime lithium-ion cells? Avoid large volume changes in the positive electrode materials. I'll show you why that's important. Use the best graphites. The graphite electrode type matters a lot. Use appropriate electrolytes and keep the upper cutoff voltage down. So don't charge to very high voltages. All the electrolyte reactions with the positive electrode accelerate when the voltage is higher. So if you keep the upper voltage down, you can make a much longer lifetime cell. So the experiments in this talk are based on these small pouch cells shown here. They're about 220 milliamp hours. We get them made by a company in China called Lifan Technologies. We specify what the electrode materials should be and the loadings and the cell design. And then Lifan has a manufacturing line that makes these for us in 1,000 lots, basically. They're all machine made and all exactly the same. But they come to us dry without electrolyte. So we fill them with electrolyte, and that gives us control over the electrolyte additives and the electrolyte type, which influences lifetime a lot. And one of the things I'll talk about today and the data I'll show you is something we call the voltage polarization, or delta V. That's the gap between the charge and discharge curve shown here. So for a fresh cell running at maybe 1C charge and 1C discharge, the gap might look like this. And as the cell ages over time, it might take many, many years, the gap will open up. And this is a measure of the growth of the internal impedance of the cell. So we don't want impedance growth happening, so we keep an eye on this delta V. All right, so I want to talk now about the importance of avoiding large volume changes. So here I show data for NMC 532, voltage versus specific capacity, and NMC 811, and a material that has 94% nickel. And you'll see the nickel 94 and the 811, they have a plateau here around 4.2 volts. And this plateau in the voltage curve coincides with a large volume change in the material. So as you move through this material, if you look in the lower panels, in the black, we're plotting the unit cell volume of the material, the crystallographic unit cell, versus the voltage. And you can see the nickel 94 material drops precipitously at 4.2 volts where this plateau is. And the same is true for 811. There's a big drop. Whereas 532 doesn't show this plateau, and it doesn't show a very strong drop change in unit cell volume at all. So if you want to avoid this large volume change, you would charge a lithium ion cell with 811 to 4.06 volts, and then you would avoid this peak in differential capacity, which corresponds to this plateau, and you wouldn't undergo this volume change. Now, why is this volume change bad? It's bad because it can cause microcracking in the electroparticles, which opens up fresh surfaces on which the electrolyte can react. And then that leads to impedance growth and all kinds of other problems, as I'll show you here. So here I'm showing you data for NMC 811 graphite cells tested at 40 degrees C with a 3-hour charge and a 3-hour discharge. The blue, they're cycling to 4.2 volts, where they're undergoing that large volume change every charge-discharge cycle. And the black, they're going to 4.06 volts, where they avoid that large volume change. And of course, the lower voltage gives smaller capacity, but after these 2,500 cycles, they're virtually the same. And if the tests continue, the blue would fall under the black, and the black would be better. So this is 3,000 charge-discharge cycles, takes about 2 years, okay? 2 years. And if you look at the normalized fractional capacity, after these 2 years of running at 3,000 cycles, you still have 90% capacity left in the 4.06 volt cell. But most impressive is if you look at the lower panel and you look at the voltage polarization normalized to cycle 1, the cell tested at 4.06 volts has had no increase in internal impedance at all in these 3,000 cycles. It's incredible. And the cell that's going to 4.2 volts has had a doubling of its internal impedance. Well, that's bad, right? So if you want to see the data, you can look in these particular papers, more explanation. So many in the audience will be sitting there saying, hey, wait a minute now. Everybody knows that lithium iron phosphate graphite cells have a much longer lifetime than NMC graphite cells. So what are you doing up here telling us about NMC graphite cells? Are you just wasting our time? And conventional wisdom is not always correct, as you'll see. So here on the left side, I show testing results again at 40 degrees centigrade for LFP cells running at a 3-hour charge and 3-hour discharge, and also for NMC 811 cells going to this 4.06 volts, avoiding the volume change. So in red, we have lithium iron phosphate graphite cells, 1,000 cycles at 40 degrees C to reach 90%. And those have the normal electrolyte salt, lithium phosphorus hexafluoride, that we all use in lithium ion batteries. But if you change the electrolyte salt to this lithium bisfluoro LiFSI, as it's called, you follow the blue curve, and you get about 50% more charge-discharge cycles to 90%. It's much better. But look, when you compare it to the NMC 811, it's worse by about a factor of 2, okay? So don't think that LFP is super good. But then you might be saying, wait a minute, you're just a university professor. Surely companies can make a better LFP battery than this NMC battery. So, who says we can do anything right? So in this panel, in red, is the best commercial LFP battery that we have ever tested, shown in red dots. It's underneath the blue and the black. And the blue and the black are our LFP cells with this LiFSI electrolyte salt, which match the best in the world. And they're still worse than NMC 811. And here, they're worse than an NMC 532 cell, the top one, operated to a voltage of 4.3, where electrolyte oxidation reactions should be occurring. This is tested at 40 degrees centigrade again for a year, okay? So the experiments on this previous slide raised some very important questions. LFP is a low voltage system charged at only 3.65 volts. Why is it worse than NMC 811 operated to 4.06 volts and NMC 532 operated to 4.3 volts? At these higher voltages, the reactions between the electrolyte and the charged electrolyte materials should be much more severe than in the case of LFP. So this actually is one of the most important puzzles that my group is working on at this moment. LFP is much better when LiFSI is used. I showed you that. What would happen if LiFSI were the only salt in NMC cells? LiFSI yields issues with aluminum corrosion at elevated temperatures when the full cell voltage exceeds about 4 volts. Okay, so what would happen if we made NMC cells balanced for lower voltage and then used LiFSI? What would happen to their lifetime? Let's take a look. Yeah, so before we do that, let's talk about whether it's sensible to make these NMC cells that are balanced for low operating voltages. So here I show the stack energy density in watt-hours per liter. This is the energy density of the graphite separator, positive electrode separator, electrolyte stack in a cell. And LFP is shown here by the horizontal line. Its stack energy density doesn't depend on the voltage above 3.5 volts because that's fully charged. So about 650. And NMC, any of these NMCs or NCA materials made into a cell balanced for 3.8 volts has a higher energy density than LFP. If you go to 3.9, it's higher, and so on. So the point here is all conceivable NMC graphite cells have a higher energy density than LFP, even when they're constructed with a balance of 3.8 volts. And if you think about it, at 4.1 volts, you have about 1,000 watt-hours per liter. If you go down to 3.8 volts, it's over 700. You give away about 27% in energy density. But what happens if you get a factor of 10 in lifetime? Maybe that's worth having. So it turns out we had some single crystal NMC 532 artificial graphite cells that were balanced for 3.8 volts, and we decided to try them with this LiFSI electrolyte salt. So just to show you what the electrode stacks look like in those cells, this is the LFP graphite electrode stack, the graphite separator, positive, just sort of a cartoon showing the relative thicknesses. This actual cell had a stack energy density of 425 watt-hours per liter, and the NMC 532 cell had an actual stack energy density of 495. And what we mean by balanced to 3.8 volts is if you take a look at the positive electrode voltage versus capacity curve and the negative electrode in the dashed line and the full cell curve in black, when the full cell reaches 3.8 volts, the graphite is full. Okay, so that's what we mean by balanced to 3.8 volts. Now, both of these cells that we're going to compare have exactly the same graphite in the cell. Okay, so this is a very busy slide. I really just want to concentrate here on the upper right panel that you see here, okay? So these triangles that you see represent the normalized capacity in the cell versus the testing time in months, where all the testing is done at 3-hour charge and 3-hour discharge. So the triangles are for lithium iron phosphate cells with lithium PF6 electrolyte salt. And I showed you before that when you changed to lithium LiFSI, things became better, and they do. This testing is at 70 degrees centigrade, by the way. It's hugely, way beyond where you would ever think about testing lithium ion cells. And then the NMC 532 cells balanced for 3.8 volts with LiPF6 electrolyte salt are shown here in these purple circles. And then finally, these orange diamonds show you NMC 532 cells with LiFSI electrolyte salt. It's incredible. They've lost only 5% of capacity in half a year at 70 degrees C. It's crazy. So these NMC 532 cells balanced to 3.8 volt only lose 5% capacity in 6 months of testing at 70 degrees C. There's almost no Impedance growth, I forgot to show you that. So down here we're showing the normalized difference between charge and discharge voltage, and it's not growing at all. So there's no impedance growth in these cells at all. There's also no gas generation. In a pouch cell, you can see the gas by the pouch puffing up. And no transition metals found on the negative electrode when you take them apart and look for transition metal dissolution that ends up on the negative side. It's incredible. So we want to know how long these things are going to last at ambient temperature. So what we do is we do testing at the same 3-hour charge and 3-hour discharge at different temperatures. And what you see here is about 1,000 charge-discharge cycles for cells operated at 70, 55, and 40 degrees C. The cells at 40 degrees C, you know, how long are they going to go? It's beyond the capability of testing them. So you have to take data at different temperatures, 85, 70, 55, and 40, and then use that data to extrapolate to lower temperatures, and we use Arrhenius kinetics for that. And for the method that we use, you can find it in this particular paper by Ahmed Eldasaki. And this extrapolation may or may not be valid, but it's really the best we can do apart from actually putting them on test for an incredible length of time. So in this graph here, I show you the time that it would take for the battery to reach 80% of its initial capacity, assuming continuous 3-hour charge and discharge cycling, plotted as a function of temperature, for different cell chemistries, okay? So the million-mile battery that we started this talk speaking about is shown here in this heavy line. So at about 20 degrees C, it would last 20 or 30 years, which is consistent with the lifetime projections that we made earlier. And then this battery that we've been talking about now with NMC 532 and LiFSI electrolyte salt, balanced and operated at 3.8 volts, this is the lifetime versus operating temperature plot. And at a temperature of 27 degrees C, it would last 100 years. So you could call this thing the century battery if you like. So what's actually the difference between the million-mile battery and the century battery? It's almost nothing, really. It's a change of the electrolyte salt and operating at lower voltage. And that just boosts the lifetime up a factor of 10, okay? So even if these extrapolations are not valid, I still believe it will boost the lifetime a factor of 10. And then where's LFP on this chart? LFP with LiPF6 is at the bottom, and LiPF6 with LiFSI is this curve right here, okay? So this is pretty incredible. Now, if there's lithium-ion people in the audience, and I know there's a lot of you, you'll notice that there's this test data at 85 degrees centigrade over here. I just want to highlight that for your benefit for a second. See that red? 85C, okay? Look at the capacity retention. 1,600 hours of testing at 85C, no gas in these pouch cells at all, 96% capacity retaining. These cells, this should blow your mind. It blew my mind. I couldn't believe this was happening. And it's a simple cell. Anybody can make this. Single crystal 532, artificial graphite. The solvents are just ethylene carbonate, dimethyl carbonate. The key here is the salt is LiFSI and low voltage operation, balanced for 3.8 volts, appropriate electrolyte additives. Anybody can make this thing. And anyone can tell it's going to last a long time at room temperature. And the real thing is, for sustainability, we have to make LFP cells that are this good. And once you see this data, you say to yourself, okay, I have a huge challenge. I have to make LFP this good. And it's not just me, it's all of us. So, these excellent lithium-ion batteries, we have to take advantage of them for energy storage. Vehicle to grid. The vehicle is undergoing charge-discharge cycles while it's parked, okay? So the utility is going to pay you for access to your battery when the vehicle's parked and plugged in. And you might say, you know, why do we need to do this? Well, the reason is we have to get more solar and wind on the grid. We need battery storage to do that. And where are all the lithium-ion batteries going to be? Well, this is a projection by Christophe Pilot from Avicen Energy. And in 2030, 90% of all lithium-ion batteries produced in 2030 are going to be in vehicles. This little tiny bar here represents those targeted for energy storage. So if you want to capture the solar and wind possibilities, you've got to connect these vehicles to the grid. And when you do so, you're going to want batteries that have a long lifetime with 10,000 cycles or more, so that the total vehicle driving range is not impacted by this vehicle-to-grid operation. Conventional wisdom, as promoted by some battery and EV makers, 100% depth of discharge cycles is enough for an EV battery. Well, if you get 500 kilometers per cycle, this gives you 4,000 kilometers of driving range total. And by then, you know, likely the rest of the car might be falling apart. But in vehicle-to-grid operation, vehicles will be charged and discharged when parked. Maybe 1 or 2 partial cycles per day. And 800 cycles is not going to be enough. So you're going to need the order of 10,000 cycles or so to really do vehicle-to-grid well. Okay? And it's possible to make batteries like this, and actually even better batteries like I showed near the end, right now. And the driving range of such vehicles will be on the order of 400 kilometers. So a number of key automotive manufacturers have announced vehicle-to-grid plans: VW, Nissan, and Ford. You have to ask questions. Are the power utilities going to be ready for this? Will the building codes mandate bidirectional EV chargers in new construction? There's a lot to think about. Fortunately, people are thinking about it. So on April 20 this year, the DOE announced first-of-its-kind collaboration to accelerate vehicle-to-everything technologies. So this is a really important first step. Here they recognize that by 2030, there should be about 130 million EVs, and I'll estimate an average pack size of 40 kilowatt hour. A lot of them will not be in North America, where the average pack size will be less. And this represents a total of 5 terawatt hours of storage that you could access if these cars were coupled to the grid. Benchmark Mineral Intelligence projects 6 terawatt hours of lithium-ion battery production in 2030. Christophe Pilot says 2. So somewhere between 2 to 6 is what the battery guys are saying, and it matches the number in this DOE report, which says 5. And down here at the bottom, I can't read it. It's too far away. But anyway, it basically points out all the benefits of doing vehicle-to-grid. You can put more renewables on the grid. The vehicle owner can get payback for putting their car on vehicle-to-grid. And it means the utilities don't have to buy these assets themselves. So why do we need such awesome lithium-ion batteries? I've talked about vehicle-to-grid. If you're doing grid energy storage directly, daily storage is about 400 cycles a year. 10,000 cycles is 25 years. I'm talking about store during the day when the sun is shining and deliver it back at night when there's no sun. So 10,000 cycles, 25 years. These long lifetime batteries will allow you to delay and avoid recycling for a long period of time. And you can put the EV batteries, when the rest of the car dies, into a second use. I believe this is extremely important. And cells and packs should be designed appropriately to encourage second use when the batteries still have life at the end of the time in the vehicle. And another challenge is that once the lifetimes of lithium-ion cells are approaching 50 or more years, it's relatively certain that the chemistry in the cells will last longer than the cell casing, the module hardware, and the BMS. Well, this is another important challenge. We're seeing it now in our lab. Chargers are failing before cells are failing. Okay. So the take-home message here is lithium-ion batteries can be extremely long-lived. It's very important to recognize this, select appropriate chemistries, and think about how these long lifetimes can be best exploited for society. I can't go forward for some reason. Here we go. So there are some very daunting numbers to think about. 160,000 terawatt hours per year need to come from renewables. Those are 2019 numbers. If you take this 160,000 terawatt hours and divide it by 365, 400 terawatt hours approximately per day would need to be stored in the event of no sun or no wind to be delivered back. And if you're doing all this storage with batteries, 400 terawatt hours of batteries would ultimately need to be deployed in 2050 or whenever. And the longer they last, the fewer need to be recycled, and the fewer one needs to make every year. If the batteries could last 100 years, then for this 400 terawatt hours in steady state, you only need to make 4 terawatt hours per year in steady state. And that's a number that's very close to what we're talking about in 2030. The factories will be making 6 terawatt hours. This is why we need long lifetime batteries, okay? So do we have the resources to do this? So a lot of people are already worried about, the availability of lithium, nickel, and so on at 2030 and beyond. And the periodic table is all we have to work with to build better batteries. Here I've just highlighted all the elements in the periodic table that are an abundance of over 20 parts per million in the Earth's crust or the atmosphere. So the periodic table becomes very small. And I think it's true that in 2030, 20 parts per million will be enough, and we'll have enough lithium and nickel and cobalt and manganese and so on to do the job. But by the time you start deploying these 400 terawatt hours of batteries, you start to worry about whether this will be enough. Maybe you need an order of magnitude more material. And if you ask the question, what elements exist at over 200 parts per million, this is what you see. There's the periodic table with the elements, I think, that are available at scale to electrify everything. And there's no lithium, there's no nickel, there's even no zinc, okay? Well, the ones I've highlighted in boxes, sodium, manganese, iron, and carbon, you can use hard carbon to make a good negative electrode for sodium-ion batteries, and you can make a pretty good positive electrode for sodium-ion batteries with sodium, manganese, and iron. So it's pretty clear to me that we need to work to get this kind of decades-long lifetime from sodium-ion batteries, and let's get to work. A lot of graduate students come to me and say, what should I focus on? Students from other universities or people I meet at conferences, and I tell them, there you go, okay? Thank you for your attention. So I see Eric's coming up here. I think we're going to have oh, don't show that. Take that away. Take that, don't get this. What are you doing? Who's doing this? Yeah, there we go.
Thank you, Jeff. That was a remarkable presentation. And now I would like to introduce ECS Secretary Marka Duff to moderate a very special question and answer dialogue with Professor Dahn. Jeff, you want to take the middle seat over there?
Sure, thanks. All right. I'm going to take a water, too. No, one will do.
Mark, you need to go over there or I guess you do.
I'll sit here. Well, thanks very much for the very interesting talk. We are going to open up the floor to questions. There are microphones set up in the aisles. And so if you have a question, please line up at the mics. And meanwhile, I'll start things off. So you listed as a thing to work on is trying to make lithium iron phosphate batteries as good as some of the batteries you were showing with the layered metal oxides. How would you go about doing that, or do you think the problem is intrinsic to the chemistry of lithium iron phosphate? It's a two-phase system, right?
Well, you know, I'm not going to tell you what we're doing in our lab.
Okay.
That's the first thing, okay? Because that wouldn't be smart. And lithium iron phosphate, you're right, it's a two-phase system. But generally the particles are very nanoscale, so that there's really not much of a problem with that two-phase system in a 100 nanometer particle. So I'm not sure that that's the problem, okay? So I'm not going to give you a lengthy answer other than to say, I believe it can be solved, but I don't know how to do it yet.
All right. But worth working on.
Absolutely, for sure, it's worth working on. You know, a lithium iron phosphate battery is iron, phosphorus, they're so abundant, you know, and this is what you would want for long lifetime cells in grid storage applications and vehicles for vehicle to grid.
Yeah. Yeah, the ability to avoid nickel and cobalt, I think, is a selling point for lithium iron phosphate, right?
Yeah, it leads to a lower cost system. It's more sustainable, and you know, it's a good battery for many, many applications, including vehicles.
Okay. Well, I think I see somebody in the audience here, so please go ahead.
Jeff, thank you for the very insightful, inspiring talk. It really breaks the conventional wisdom, in my mind at least, that LFP is not as good as, cannot be better than NMC if you do that right. So it seems that from your talk, one of the key components is lithium FSI. And I know that there are some rumors flying around, at least among the battery manufacturers in China, that they are completely replacing the lithium PF6 with this salt. So my question to you is that where's your source of the lithium FSI and how important the purity level is?
Is the question how important is the purity?
Yes. Where did you get your FSI?
We get our LAFSI from a reputable supplier.
Another question, if we, by some luck, we invented in our lab a battery which never dies, is that good for the battery industry?
I'm having a lot of trouble understanding. It's kind of like an echo chamber at this side.
Yeah,
maybe one of you can help me.
Yeah.
I'm going to come a little closer so I can hear you better.
So suppose that we have a battery which never dies. Is that good for will that drive the battery industry to bankruptcy?
We're going to bankrupt the battery industry? No. No, I don't think we're going to bankrupt the battery industry. We have to electrify everything. You know, I told you, 400 terawatt hours of batteries have to be deployed, right? And any kind of battery that can walk, skip, jump, that's sensible, we need them. It's a war on climate change, you know? That's what we're facing here. And it's time to start thinking about it at the scale that I'm talking about, right? If we want to make it work.
Thank you.
Okay, we have somebody here to my left. Yeah.
Hi, Simon O'Kane, Imperial College London. Thanks for the excellent talk. Regarding the performance of the NMC 532, have you tried the balance to 3.8 volts? Have you tried similar experiments on the nickel-rich materials that don't use as much cobalt?
Yeah, so that's a good question. So the question is, have we worked on similar cells operating at relatively low voltages with higher nickel materials? The answer is yes. We have cells with 83% nickel that are operating, they're balanced for low voltage, and they're operating very well under this circumstance.
All right.
Just didn't have data to put, I didn't put data in the talk. I wanted to, focus on the 532 where we had data operating up to 4.1, 4.2, 4.3, and then show what happens if you lower the voltage down and put in LiFSI.
Thank you very much.
All right. Please go ahead.
Yeah, Martin Winter from Münster. Thank you, Jeff. Again, very educational and also entertaining. Can you understand me well?
It's like an echo chamber at this side. I
Okay.
seem to be able to hear you better over here.
Good. My question is, first of all, I want to say I haven't seen such cycle number before. I think the only one I remember was with the supercap. So that was very nice. When you are thinking about where our application areas are going, basically you brought two together, that it was grid storage and electric vehicle driving. And for grid storage, I fully understand that this enormous life, both during, let's say, during time, century, but also for going the miles, I think it could be important, especially when you go to a vehicle to grid. But our automotive industry actually would like to go for long driving ranges and fast charging. This lithium metal, solid state, high voltage, high capacity materials. So how much of capacity and energy do you give up for an NMC-based cell when you are staying at 3.8 volt? And will this be, let's say, it's good enough for, let's say, the grid storage, but will this be good enough for 500 kilometers?
Yeah, I get the question. So I showed you on one chart that we give up about 27% stack energy density from a 532 cell operating at, or a high nickel cell operating at 4.1 to 3.8. So the question is, how high can you push the voltage and still use LiFSI? Would it be okay at 3.9? So I showed at the Florida meeting microcalorimeter data that measure parasitic heat flow as a function of voltage. And between 3.8 and 3.9 volts for this NMC chemistry, the parasitic heat flow is flat. So I think you can maybe go to 3.9. So then it's probably a 18% penalty, okay? So an 18% drop in driving range. So then I know the vehicle industry is pushing this long driving range. In fact, there's a Lucid Motors showroom not far from here that we stopped in on our way to the conference. We entered, the salesperson came up to us and said, "See this car? It can go 1,000 kilometers on a charge." That's the first thing he said. So this is what people want. But the question is, do they really want it, or do they not know what they want? If you own an electric vehicle and you think range anxiety is a problem, the vehicle tells you exactly how far you can go before you need to charge. There's no range anxiety. It's called planning, okay? That's what it is. You can, if you have a charger at your house, you can leave the home 70% charged if you're not going so enormously far or a long trip, charged 100%. I think 400 kilometers is a reasonable amount of range for most people, And those batteries can be these incredibly long lifetime things that are well suited to vehicle to grid. Of course, if we could figure out a way, and it's a huge challenge to make 1,000 kilometer car batteries last for this amount of time, that would be wonderful too, right? But I think that's going to be tough. It's going to be tough,
We have another questioner over here.
Hi, Shannon Betcher, University of Oregon. You can hear me?
Yeah.
So my question has to do with what your thoughts are when you start talking about long duration energy storage, seasonal energy storage, where you just don't have 1,000 years to cycle the battery 1,000 times, right? If you cycle once per year and you need to amortize the cost of this energy storage device. So is there a role for sodium or lithium ion batteries in this sort of piece of the puzzle, or does it have to be something else? I'm curious to your thoughts there.
Yeah, this is a real tough question. What do you do about seasonal? This is really tough. And I don't have an answer for that. I can tell you as a solar panel owner, and Eric is one too.
And me too.
And Marka, when you look at your output of your solar panels in January compared to June, you just go, it's down by a factor of, well, for me in Nova Scotia, about a factor of 6 between January and June. So does it mean that you have to put 6 times as many solar panels out there to deal with the winter time? Fortunately in Nova Scotia, in the winter, the wind takes over. So we're down in solar, but we're way up in wind. And maybe that's the case in a lot of jurisdictions, I don't know. But seasonal is a problem that is a problem.
All right. We have someone else here.
Yes. Chumei Ban from Boulder. I have a question related on slides when you compare lithium iron phosphate and NMC materials. When a voltage of a 3.8 applied for these two systems, I feel more than 98% of lithium participate into the lithium iron phosphate system. However, less than 50% of lithium participate in the NMC. So for this two systems, and for lithium iron phosphate, there's a lot of lithium actually have to leave the system and come back. The material actually definitely is showing the very different system. So I wonder, what do you think about this? This is actually applied for most of the materials because we actually fully use the lithium in the system. And that is probably one of the reasons for this degradation or never improve the lithium iron phosphate if we are using 98% of lithium there.
Yeah, I understand the question. So you have to realize that in both systems, you're using the same graphite, and in both systems, you're exercising the graphite 100%. The graphite is being completely filled, and the graphite's being completely emptied in both systems. And in both systems, the degradation mechanism is loss of lithium inventory at the negative side, okay? And by limiting the voltage to 3.8 volts of the NMC system, all that other lithium, we never touch it. We never touch it, right? So you say there's extra lithium, but I say, fine, but we never touch it. We don't use it.
I say, how about single crystal? Have you tried the single crystal lithium iron phosphate?
Well, what is single crystal lithium iron phosphate? I mean, what we use is lithium iron phosphate that are very small nanoparticles, 100, 200 nanometers, and they're all single crystals at that size. So I guess we are trying it, but they're small.
NMC is more than micrometer, is that?
Oh, heck. There's a lot of troubles using large-sized lithium iron phosphate. The lithium ion diffusion constant within lithium iron phosphate is very, very slow. So a big primary particle of lithium iron phosphate would have very terrible rate capability.
Thank you.
Go over here next.
Hi, I'm Jeff. Great talk. I would like to ask you about the next generation of batteries. Are they needed? So it seems that you solved a lot of problems already.
I'm having trouble understanding.
Oh, okay.
I'm going to come right down next to you. And you can speak in the mic so they can hear, but this way I can hear too.
Okay. So I'm asking about your kind of your thoughts about the next generation of batteries, like all-solid batteries, aqueous batteries, because currently lifetime probably solved or would be solved, energy density is okay, so, but still safety is an issue, and we need probably more energy-dense batteries for some exotic application like aviation. So what's your thoughts about that?
Yeah, okay. So the question is, what are my thoughts about all the other alternative battery technologies that are under development?
Two people here.
I think it's great. We need every kind of battery that we can possibly get. You know, he mentioned aviation, so we need some very high energy density batteries for for aviation, for sure. So let's go and make them. And we need other battery types besides lithium. We need zinc manganese dioxide. If it can be made long cycle life, it could be wonderful, right? Solid state. If it delivers as promised, it's going to be wonderful, right? So all these things that are underway, if they succeed and can be produced at a reasonable cost, that's good. So I think all of it's good. Let's make it work, right?
All right. I think we have time for one more question, so I'm going to make you run over here.
Sure.
Hi, thanks. Penelope Jones, Cambridge. To what extent is the cycle life impacted by the charging rate? And what would you say are the biggest factor? Oh, sorry.
It's like if you stand up there, it's like an echo chamber.
Sure. To what extent is the cycle life impacted by the charging rate? And what would you say are the biggest factors affecting the maximum charging rate? Thanks.
Yeah, so the question is, what are the factors that affect the maximum charging rate? And what could be the maximum charging rate, I guess. There's a lot of factors that affect the maximum charging rate. Most importantly, the design of the cell, the electrode thicknesses. So in our cells, the electrodes are about 4 milliamp hours per centimeter squared, so the loadings are 22 or 23 milligrams per centimeter squared. And you know, in that case, we can charge at room temperature, depending on the electrolyte, at 2C or so. If we wanted to charge faster, we'd thin the electrodes down, or we'd crank up the temperature. So I didn't show you data, but at 85 degrees C, you can imagine what the electrolyte conductivity is like at the lithium ion diffusion constant. So these cells I showed you at 85 centigrade, if you run them at a 6C charge and 6C discharge, again, 1,600 hours, you lost about 5 or 6% capacity, but you've racked up 3,000 or 4,000 cycles in this 1,600 hours. It's crazy, you know. So you can always design a cell for fast charge. Just make the electrodes thinner. You have to give up energy density, but you can always solve that problem if it's important to you.
We'll take another question. So at least it's on the same side of the room.
Hi, Sharon Chen from Research Officer from National Research Council. I'm not actually in the area of the lithium-ion battery, but just one actually general question about right now the electric vehicles are still expensive, and people like me can still not afford like a Tesla car. I'm wondering like how long does it take actually to lower down the price of the battery, and actually even people actually at like a minimum wage can afford one.
Yeah, so that's a wonderful question. It goes beyond my knowledge. You know, how long is it going to take to really lower the cost of electric vehicles? You know, the targets for battery pack costs, if they're $100 a kilowatt hour and you have a 50 kilowatt hour pack in your car, that's a $5,000 battery, okay? So I don't think you can blame the high cost of an EV entirely on the battery pack, okay? Because the battery folks are getting the cost down to the levels where the battery's a $5,000 component in the vehicle. So It's the other parts have to come down as well. So I don't know how to answer your question other than to say, I think from the battery side, we're getting the cost into the right ballpark.
Does it work? Yeah, okay. I guess then, the EVs, they should actually work together to make the cars that can be affordable to most of us. Thanks.
Thanks.
We'll take the last question or here.
Here? Here.
Hi.
Okay.
Hi. My name is Natalie. He's my dad. I don't have a college degree. I don't have a GED. I am just about to graduate the 6th grade. I didn't understand half of your presentation. Sorry. But what?
It's really hard to hear up there.
Sorry. But what I do understand is that clean energy is really hard to push on a lot of the countries, thanks to a lot of the stuff that my father watches. How clean energy is a really big problem in the US because not a lot of, majority of Congress, or the people who control Congress, aren't very big on supporting clean energy. In fact, most of them have large donations from fossil fuel industries. How would you help, or not help, but rather, how would you make it in a way that the countries that could support your plan want to support your plan?
Well, that is a wonderful question. You know, and this is where the society like the Electrochemical Society can step forward and you know, lobby governments and so on and say this is important to do. The fact that the Department of Energy has recently recognized the importance of vehicle to everything, as I mentioned near the end of the talk, I think is a really good first step along the way of you know, really trying to electrify everything, and that's where we need to go. How do you get the average politician who has made a lot of money off oil and gas, if that's the case, to believe in this thing? I don't know the answer to that question. I think that the real key is you have to elect the right people, right? And, well, I'm happy I don't live in the United States.
I'm unhappy that I do.
Because, you know, recently you definitely elected the wrong person as president, the previous one.
So I just want to comment when I made my introductory remarks earlier on, and they showed pictures of me and my history with ECS. One of those pictures was my walking, holding my daughter's hand to the first ECS meeting she attended when she was 1 year old. So this is what ECS does to you.
That's your daughter?
That's my daughter.
Awesome.
What a budding electrochemist.
Great.
All right.
Good. I don't know how to follow that.
No, I don't either.
Jeff, on behalf of the Society, I want to thank you for that amazing presentation and the dialogue. Marka, thank you for leading that. I think we talked some amazing technical issues, and I think we got into the very bigger issue of what we're trying to solve here with ECS through our science and what we're trying to do for the world, and really the importance of this organization. And so on behalf of ECS, we want to present you with the scroll for the presentation today and for your groundbreaking work. And I know you've been a member for 30 some odd years at this point, but now you have earned honorary awarded life membership with us. So you never need to pay a due again. Yes. So thank you very much, Jeff. That was fantastic. All right. All right. Well, in closing, I would like to say thank you to everyone for participating in today's ECS award ceremony and plenary lecture. especially Jeff and Marka Duff and Eric Waxman, our president. Before we wrap up, I should mention that the 242nd ECS meeting will be held in Atlanta, Georgia from October 9th to the 13th, and you can see our other future meeting dates on the screen right now. I would also like to invite ECS members to join us tomorrow at noon for the annual Society Business Meeting and Luncheon. You may purchase tickets at registration. There's a few seats left, so if you do want to attend this, don't wait. They may be gone. And most importantly, the exhibit hall is now open right next door in the West Ballrooms B, C, and D. Join us as we open the technical exhibition and host tonight's first general poster session. I know the exhibitors are very excited to see you, as well as the poster presenters, so please make your way over there immediately following this. They'll be eager to see you. And thank you, everyone. It's so great to be back to in-person meetings. It's so wonderful to see you. Thanks again to Jeff Dahn. Have a great meeting, everybody. Thanks so much.